you so much for kind introduction. My name is Regina Lee. I am a Canadian among many Americans. Oh, wait, it is being recorded. Can I start over? I was in Texas until yesterday, and I was really nervous going there, coming back and coming into this whole presentation. I was actually a little nervous about it, and I really appreciate the opportunity. And I sincerely thanks for the opportunity to actually share my passion about space. When I first submitted my abstract, I actually wanted to talk about the image processing, but I realized that it'll be a very wide audience, and except for 박우상 박사님, probably not many of you are familiar with the concept of space debris, space garbage, space situational awareness. So I ended up just shifting my focus. Yes, there are 65 slides, and I will not present all of them. Instead, I'll be only talking about the first 20 or so slides about SSA in general. And then again, a little heads up that I do have a little bit of a Canadian content, and it's not to emphasize the fact that I grew up here in Canada, but also to just talk a little bit about myself, where I'm from, where my interest is stemmed from, and where we are actually generally heading towards. It's never been an issue up until very recently. So again, if there's a bit of a concern in terms of my content, and I apologize well in advance. But if you are interested more on the image processing side, I would be happy to share entire 65 slides with you and meet with you to discuss some of those other areas of my research. So if there's a little bit of a deviation from my abstract, it was for that reason. As introduced, I actually work with a very large group of students who are very much interested in what we call nanosatellite technologies. I actually worked in a small company before I joined York University that specialized in those technologies, including reaction wheels, thrusters, and sun sensors. And ever since I came to York in 2007, that's where I've been heading. But more recently, I've been more focused on the optical sensors rather than just the pure satellite technologies. But again, before I came to York, I worked as an attitude control systems engineer, and in those short period of time, I actually had an opportunity to work on other devices other than satellites. And to this day, some of these missions are still in operation, and I'm quite proud, and we often talk about that. So the image on the left, the little satellite that's the size of a suitcase, was the very first Canadian telescope in space. And again, it's a very small telescope. And we've been calling it very humble mission, but it actually operated for 10 years, taking pictures of stars for a long, long time. The reason I actually often start my conversation with the MOST mission is because I worked as an attitude control systems engineer, and I worked on star trackers, but we never actually saw anything that went by in our images. It was only in the last 10 years or so that we started seeing other satellites in star-filled images. So what we used to consider noise, i.e. satellites in the field of star images, now that's my research. We actually try to take out stars and only focus on the objects that's passing by in attempt to identify them and characterize them. And that's basically what my presentation is about. Launching satellites is a very, very expensive and long-term project. For that reason, as a university professor, it's sometimes rather difficult to participate in satellite missions. So for that, we've been flying our payloads and other platforms as well. We are always looking for international industry partners to allow us to fly our payloads on anything that flies. So we joke about we'll fly anything except for paper planes. And we've been able to collect lots of images. In more recent years, we've been getting a lot of requests from actually US companies and academic partners asking for those images as a basic data set. So fun fact, I just wanted to start with a few very, very cute ideas about how Canada has actually played a key role in space exploration. At the same time, I understand that we are probably the only people who are proud to be number 3 in the world. No one actually goes ever out there and say, we are number 3, but we are very proud. US was obviously number 1, then Soviet, and we were in the 3rd country to launch a satellite, and that legacy still carries on. And there's a huge research community members who contribute towards space exploration. Another fun fact that I quite often share with my students is how many active satellites are in space today. Again, I started my career back in 2000. Not that I want to talk about me being really old, but I've been doing this for a long time, since 1994, and since I graduated. and it's been many years. And when I went into space engineering as my career path, it was very rare to see more than 2 or 3 satellites being launched at the same time. But today, that's no longer the case. There are well over 8,000 satellites being active in space, and that number is changing almost on a daily basis, with companies like SpaceX and OneWeb launching spacecraft thousands at a time. Those numbers will only go up more as we continue to develop more satellites. And those are just the active satellites. If we start counting inactive debris, components, parts, like small, tiny pieces, we are talking hundreds of millions objects. And because of that, it has become a real issue in the last 10 years. And we are slowly starting to see more effort in developing technologies to not only observe them, but also to find ways to remove them from space. So often we compare this to an issue of plastics in the ocean. 10, 20 years ago, that was never a topic of conversation over dinner. But today we all talk about it, how we're going to remove those plastics from ocean, how it's causing a lot of pollutions and yada, yada, yada. Same thing is pretty much happening in space, and yet we are not talking about it, even though we are seeing the absolute increase in number of objects in space at the rate that we never predicted. What's even more concerning is the fact that the active satellites are only a very, very small portion of those objects in space. It's the debris, it's the fragmented parts, inactive spacecraft that's been degraded and has fallen apart. There has even been several instances where some countries that we don't want to talk about have actively participated in the weapons experiment. So instead of having to worry about one big space debris that's no longer active, now we are in the place where we have to track hundreds of thousands of tiny little particles that's floating in space. So it is a real issue, and we are only starting to recognize it recently, but that never stopped us from building more satellites. We literally now manufacture stamp out spacecraft in a way that we never, ever imagined. So when I took a course back in the 90s about how to manufacture spacecraft, and even though that wasn't really the course title, it was something to the effect of like space mission design, space vehicle analysis, design concept. We never really thought about building more than one spacecraft at a time. Today, when I teach a course on space materials or space engineering, we talk about how mass manufacturing has impacted the way we see space engineering. I work with a company called MDA. That's the company that built Canadarm, and it's a rather well-known international company. They're almost producing 2 satellites per day. They literally hire people for job title like production line manager or something to that effect. So PhD with the space engineering, working in a company called MDA with a job title of line manager sounds rather strange, but that's the reality. We actually do have companies around the world, in Korea too, manufacturing spacecraft like we would produce automobiles. And all these spacecrafts will go up. Recently, there has been lots of news about how Starlink satellites are now coming back, re-entering Earth's atmosphere, and they're all causing some form of a damage to our atmosphere, to our environment. And we haven't really developed technologies to protect ourselves from those instances. The damage that it causes is often recognized as the damage that happens in space, like the punctured holes and satellites being hit by little debris. And there has been many situations where astronauts had to go hide in a certain area of the International Space Stations because of the collision possibilities. But it also has an impact on our everyday life on Earth, because again, there has been a few articles of how space junk has been found in the airspace, and I think it was the Spanish airport that had to be shut down for a number of hours because they couldn't predict where the object was going to land. We also found a few objects in the middle of desert somewhere in somebody's farmland. So we are starting to see more and more of this. And that's really what got me excited about this particular area of research. And then again, my background is in the attitude control system. So I started with the star tracker as my main potential payload for tracking these objects. And that's where I've been heading. There are lots of other researchers who more focuses on protecting assets rather than simply observing it. And it's been looked at from a lot of more of like a military perspective rather than a civil perspective. So there are lots of these videos that talks about how it can actually cause real damage. Now, half of my group in my research team, I have about 20 to 30 graduate students and undergraduate students in my lab at any given time, and half of them are actually astronomers and physicists. And that's mostly because they're the ones who actually see the impact of these debris in every day. When we look up in the sky, we no longer see stars as I talked about previously. We actually see lots of streaks that's going through. And this was one image with a Starlink being launched. And I'll show a few other images as well. And that's the reality. A lot of our astronomy colleagues are spending time to remove these objects and sometimes struggle to identify them because they're quite often, frankly, not known whom it belongs to. So from the Canadian perspective, we actually did start our own version of Space Force, and then US Space Force has been in place for a long time. In Canada, it's still relatively recent, and we actually do work with that team, not necessarily to just protect our asset, but also to find other technological solutions that may one day solve some of these issues. Now here I want to just take a quick stop to look back and talk about space domain awareness as opposed to space situational awareness. SSA often is seen as an area where we are simply observing the space around our own assets. So from a spacecraft to understand what's out there, ultimately that's an idea of being able to avoid some of the more dangerous situations, to be able to catalog what's out there, whereas domain awareness is more a broader term. So it's very similar to the way we see land, ocean, and sky. So Air Force, Army, and Navy. The space is a separate domain, just like cyberspace. So cyber domain is now seen as a specific area where we need to build our resiliency, our own force, our own protection mechanisms. The space now is being seen as that. There's a lot of projects that's coming out, and I actually work with quite a few colleagues in this area as well. So SSA, once again, is really about finding solutions in congested, contested, and competitive space. And it's quite often seen as a very early stage of research. And a lot of colleagues are slowly getting into this space, coming from different backgrounds. And I can totally see that there will be twice more and 3 times more research capacity in all around the world in this particular domain as well. So I don't know how much time I have, and somebody will have to tell me 5 minutes before, because as I said, I've got 65 slides and I was only planning to talk about first 25 or so. So please do give me a signal if I'm going over time. I just wanted to take 5 minutes of this presentation time to talk about what we've been doing specifically for this effort. So the main reason we started doing this 10 years ago, about 10 years ago, is because we simply didn't have enough data. So we started going around the world. We actually worked with a team at University of Texas, and that's why I was there, who gave us precious set of data, which was basically the light curve that they collected. So instead of taking pictures of stars and planets, they actually took pictures of objects in space and collected light curve. And we used that set of data to understand what object we are looking at. So we can actually understand the spin rate of that object. It's the same way astronomers study planets. We actually try to understand the materials of the spacecraft that we are observing. We try to look at the orientation of the object that was studying. But at the end of the day, the data sets were so rare, and we really couldn't do the research that we really wanted to do. So we wanted to collect our own data. And rather than just going to a very expensive route to build our own telescope and creating a new sensor payload, we just relied on a star tracker, because we recognize that star trackers are capable of observing some of those objects in space. Instead of launching right away, we relied on Stratus balloon missions. I had a lot of hesitation about this, since it only goes up to about 40 kilometers, and the duration of the flight is anywhere between 9 to 14 hours. I wasn't too confident that we were going to collect images, but long story short, we were actually able to collect almost 100 1,000 images within the first flight. Not a cheap mission, I have to admit, but as a university team, it's actually a whole lot cheaper than doing a full satellite mission. Even a CubeSat mission would cost like 10, 20 times more than this. So in 2022, we actually did our very first mission. Up until 2022, we were doing it from ground. We would take the payload out in the field, stay up all night, taking images with a telescope and our own cameras set up. We actually had a beautiful setup with like 4 or 5 different cameras set up in the field, but it was still very weather dependent and it was time consuming. And starting in 2022, we started doing it from Stratusville, which was a very cool experience for student training, payload development, and technology demonstration, as well as the actual data collection. In 2023, we actually flew with the 4 cameras, and that was, again, the second time doing it. I think someone actually mentioned that you're an expert in thermal management. That was one of the areas that we struggled with. We basically just covered the whole thing with the thermal blanket as much as we could and hope that it doesn't burn up when it sees the sunlight. But even those little things, it became a bit of a challenge for a university team like ourselves. But again, our main goal was to collect images. And the real research was once we collected the images, we started analyzing them. We started developing image processing techniques. So that was going to be the main focus of this presentation. And that's the remaining 40 slides of it. And I would be happy to share them with you, but I wasn't sure if that would be the actual interest for this group. So once again, do let me know if I'm going over time. I was hoping to stop at 8:40, but I see that it's already 8:42. One of the beauties about, I'll just take 3 more minutes and that's it. Would that be okay?
Yeah, that's perfect. Yeah, 3 more minutes. That's perfect. Thank you.
Okay. And again, I would be happy to share my 65 slides. So our payload is relatively small. We do still stay within the CubeSat form factor. The whole gondola is size of a minivan. Ours is like the tiny little thing that sticks on the side of it. But we actually provide the attitude information along with those image collection as well. And we work with the Canadian Space Agency and French Space Agency to provide the attitude information in real time while we do our own research as well. So this is the video that we've done, but I'll just quickly go through it. Again, thermal management is of a huge concern. It does go down to -80 in the middle of the night. We didn't think it was going to be the issue because Stratus balloon only goes up about 40 kilometers, whereas the low Earth orbit starts from 100 and 200 and up. But it is a challenge that we are still struggling with. So I'm just going to leave it with some of those pretty images that we've collected on one of the many payloads. So in the image like this, we are basically looking for a moving dot, which is the satellite that we are seeing, whereas stationary dots in our yellow circle are the stars. Without any processing, we can already see 1 or 2 that's moving. This particular image sequence actually contains 23 objects. We were able to identify 300 unique objects from this sequence of images. We've seen OneWeb, not OneWeb, what am I saying? We've seen rocket bodies, we've seen various satellites. Many of them are Starlink spacecraft, just by pure sheer number of them in the sky. And that's what we continue to work on. This particular image, one of the reasons that I actually show this image is because this work was done by a high school student. The kids these days are so smart that you give them an image like this and tell them to find moving dot and they'll do it within a week or so. There are so many really good solutions out there that can actually do it. Obviously, we have postdocs who are developing much more advanced algorithms, but the fact is that we can easily identify objects, and the real challenge starts from that point on. So we are working with the Korean colleagues to do the orbit prediction from some of these images, and from there we can associate them with the actual objects. So again, we were able to find about 200 to 300 objects, unique objects from 100,000 images we've collected, and we are getting ready for the next launch coming up in August as well. So that's where we are spending, and I'll stop there. And this image is a little bit more obvious because we were able to pre-process it a little bit more, and you can see more objects flying around. So I'll stop there. This is more or less just an introduction to my research, but I thought it might be more interesting than going through the actual the actual image processing part, and that was my original slide I wanted to present, but I'll just leave it as being available to the group if